Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson. And Fred and I were talking about quality in manufacturing and how it relates to reliability. And there's a topic that I don't think reliability engineers talk enough about. And I think quality engineers tend to think they're suitably different as well, that they speak their own language and never the twain shall meet.
Well, we started talking about it, and 20 minutes later, it says, we should hit record. It's one of those where it's like, oh, this is good. And when we start doing something like that, and this is kind of the gist of the show, I think, is that it's stuff we like to talk about. So yeah, paint us weird, whatever. But as soon as you brought it up, you say you wanted to talk about CPK, and I'm like, yeah, that makes sense to me because it relates to what we do to make a reliable product. And maybe it's because I grew up in a factory. In my early professional days, it was SPC and CPK was a big deal, and we were tracking and measuring it all the time. It wasn't until later where I got more involved with the design side that I realized, oh, this is how you use it. Okay.
Right.
Yeah. Just doing CPK on a line all by itself, it's kind of nonsense in my mind. You can go after yield issues and things like that, but it's not really the end goal here. You want to get something out the door that works.
Yeah, yield is a metric that organizations who suck at this deal with, unfortunately. So, yeah. I mean, organizations do this well. They don't need to worry about it because they're in spec and they know it, and they know the likelihood that things will be out of spec because it is a random process after all, and et cetera, et cetera, et cetera. But yeah, I think there's a lot people hear SPC, which is statistical process control, and process capability analysis, which is or PCA, and there's people I think are sold that it's the same thing or close enough to the same thing, or the only people who will tell you it's different are statisticians who live for this sort of stuff.
Yeah, like me.
I think that, there's, as you know, it's a very practical difference between the two things. And the way I try and describe it using an analogy is, imagine you're jumping into a taxi or an Uber and you expect the driver to drive the car or vehicle in the middle of the lane, making all the correct turns. Essentially, when the driver turns the steering wheel, you want the car to go in the intended direction.
Yeah.
But imagine you're sitting in the back of that taxi or Uber or Lyft, and you see the driver furiously turning the steering wheel left and right just to keep it straight. And obviously there's some sort of issue with the steering pinion, or you know that the car is mechanically unsound, and the driver is having to do all sorts of things just to keep the vehicle going straight. Now, even if the car goes in the middle of the lane, you are going to have a very nervous trip or journey until you reach your destination.
I haven't had that experience. I actually have had taxis where the driver was controlling the vehicle just fine, but very erratically, just all over the place.
Yep.
Yeah. So that's a step down. Now, if it's the driver's going crazy, but very skillfully keeping it in the lane, what we know is that something's not right with the mechanics, and it's going to fall apart. But when you have a crazy driver, it's a different story. There's all kinds of stuff like that. But anyway, on with the analogy.
Right, but either way, I mean, so you imagine the passenger sitting in the back of the vehicle, and no matter how skillful the driver is at dealing with the steering wheel, which is clearly only has a spiritual relationship with where the car actually goes.
It's merely a suggestion. Yeah.
You are going to be very nervous, and a lot of things will go through your head, like, well, if it's this bad now, how bad is it going to be 1 mile down the road when I'm on the 401 at 100 miles an hour? It's not a good feeling, and it's actually a very rational feeling, because you can see that there is an element of your car being out of control.
Yep.
And that's what SPC is all about. SPC is essentially where before your vehicle starts veering off the road, you detect that play in the steering wheel or detect that play in the brake pedal, or you can just start sensing that something is wrong with your vehicle well and truly before it goes off the road. And when you sense play in the steering wheel, that's when you take it to a mechanic to get serviced, to get repaired, and that's how you keep your car driving on the middle of the road. But the problem with many organisations, if they're in the back seat of that vehicle and the driver is clearly struggling to keep the vehicle straight, but perhaps fortuitously they are, well, many organisations say, "Oh, that's cool. We're cool. We don't know what the manufacturing process is doing. It's doing weird stuff, but as far as we're aware, there's no defects, so there's no problem, no harm, no foul."
Well, there's also, they'll put in workarounds and added steps and extra controls and just add it. I've seen it where they have an erratic process, and so they add all these filters and conditions and workarounds to it. So then they end up with a very complex system for what should be a relatively simple manufacturing process.
Right.
And it's like, no, you don't need to do that.
Maybe that workaround is analogous to another person who the driver brought along, who's in the passenger side, who is leaning out the window and has an additional wheel on the end of a post trying to additionally steer the vehicle. I mean, that's the workaround. Yes, it might help a little bit, but it's outside, let's just say, the spirit of this fit for purpose.
Yeah. Vast majority of the time, whether we're cutting holes or aligning stuff or assembling things or soldering or whatever, there are usually pretty well-defined processes. Now, sometimes you invent something just exotic and you haven't figured out how to make it twice in the lab, much less anywhere else. We're talking about ones where you're making something every day over and over again and in an ideal world. Now, there are ways to deal with this with small batches and everything else, but if the machine is supposed to cut a hole that's 2 millimeters in diameter and it's round and everything else, that's what it should do. Now, that we're not talking about when somebody tries to use that drill bit to make an oval by now using it instead of as a mill to cut the side of it, is you just push the blade across where it's not designed to do something that's out of its capability from the equipment's design. Set those aside because there's plenty of those issues out there too. And I think SPC is showing you that you have such an erratic process that you have this crazy driver trying to keep everything under control is, well, maybe you have a fundamental problem with your process that you're pushing it outside of its range and yelling at it and adding more controls and adding more pressure to the system. It's generally not a good process or good technique. Well, but let's say you have good equipment, you have good operators, but you just aren't keeping track of what's working or not working. And like you said, in the analogy is as the steering gets looser, and I've seen it where operators will go, well, that's not quite right. Let me up the temperature. Let me change this. Let me change that. And sometimes their experience says, when this happens on a cold day, I do this and it brings it back in line. But other times it's pretty random, especially when engineers got involved. Then they were just trying all kinds of weird stuff.
Right. Well, I mean, the thing about workarounds is I tend to only see workarounds when they were the solution to a crisis. And what happens usually is that organisation, that CEO or the head quality guy, is analogous to that passenger sitting, or that driver of that vehicle going instead of taking his or her vehicle to the mechanics to get fixed when he or she first notices some play in the steering wheel. Instead of doing that, they say, well, I can still drive the car, so everything's okay.
Yep.
And so when you do that, things get worse and things get worse and things get worse, and all of a sudden, you come a day where you have to do something else in order for you to do your work for that day, or the cost has become now so prohibitive that because you've let your vehicle degrade to such an extent, now the repairs are thousands of dollars, that you have to shortcut the system. You have to try and find a solution today in order to get your vehicle out in the road to make money, because this is for this is.
I've seen it where, I mean, with that kind of scenario where the 3 different shifts with this one factory had markedly different yields. And one shift just didn't measure anything, so everything shipped. Right. They had great yields. Another group, it was a temperature-sensitive system, so they would play with the temperature to bring it in spec when they measured it. Right? And the third group was kind of doing it by the book, and they had horrible yields. But they're the ones that got in trouble and kind of got, well, how come you're not doing what the others are doing? And it was not with an understanding of what was actually underlaying the process. And until a handful of us got involved and started watching exactly what was going on and how they're doing it and knowing the details of the product and going, you know, if you go put it out in the sun, this measure that you're doing will change and it'll move it. Yeah, we figured that out a while ago. So we heat it up to get it in spec and then we ship it. Okay, let's think about this. You know, and another group, they gave up measuring it because they said it's pretty random. And they were using a system that they had modified the probes to be 2-point contact to measure resistance when it should have been 4-point contact. But it's not obvious in the probe. When you look at the two of them, one had a red hinge and one had a blue hinge. Right. But they're saying, you know, when Sally measures it, it's in spec, but when I measure it, it's not. So this is a worthless measurement system, so we're not even going to bother. Okay. So we don't, you know, so there's bigger pieces to it. If it's outside the analogy, is if you have a piece of equipment or a process and you've had the team, you know, engineer it, you've qualified it, it created a good product for a while, but over time it degrades or it changes or your materials change or your processes change and it just adds up and adds up and adds up. Now you're out of control. You know, and that's kind of it's a slow process. It might take years, but it happens in even the best of processes unless there's something to monitor it, keep it under control, and keep that in. And I think that's the role of SPC, right?
Correct.
Is it consistently performing the way it should perform? But that's not what we came here to talk about because
No. Well, in a way, I mean, your example there, that organization had plenty of warning that something was amiss if they wanted to look for it.
They didn't, yeah. And that's a different issue altogether. That's a whole nother problem. So let's say you're paying attention to your process, you're paying attention to SPC, and you recognize that something's not right. You get it in control. The driver can relax, doesn't get quite the aerobic workout driving down the road. And now, and that's the hardest part with many, many processes to start using these systems is to actually get it in control, to be consistent, because there's so many variables that can affect you to get your disconnecting your steering wheel from the wheels kind of setup. And I find that that's frustrating for some people. We've been making these products for years. It's just, yeah, but you have 50% repair rate on these things. You know, that's not consistently making your products. Let's make them so that you don't need to do the repairs. But once you get all that set and you get to a process that's humming along, the driver's just barely, you know, keeping the car in the road with normal gyrations on the steering wheel, that's where CPK comes in, right? It's not, you don't just do CPK on a random process. It has to be in control. Right.
There's no point in measuring where an out of control process is, because you come back the next day, it's going to be somewhere else. There's no point.
Yeah.
But for those of you who don't know what CPK is it's what we call a capability index, and it measures the extent to which the variation of some characteristic is within specification limits. So if you're drilling a hole, the diameter of the hole needs to be 10 millimeters, plus or minus 0.02 millimeters. So CPK is a measure of the extent to which the variation of your manufacturing process, your drill press, creates holes which are within specifications.
Right.
And it's part of this where Six Sigma acolytes cut their teeth. And it's statistically, it's based on the normal distribution, which is a problem because not every process is normally distributed, but a good number are. And the idea is that, for example, a characteristic with a CPK of 2 means that 6 standard deviations of variation are within your specification limits.
Right.
A CPK.
And CPK is a little bit different than some of them because it takes into account, is it centered? Is it within the range? Is it close to the target? Because you can have really tight variability, but if you're over in left field someplace way away from where you're supposed to be drilling, you can still have a great CP. It's a different measure, but it only measures the relationship between variability and spec.
Right. And in a CPK of 1 is one where he's got 3 standard deviations within the specification limits.
Is that plus and minus?
Yeah, plus and minus, we should say. That's correct. Yeah. Sorry. Yeah. So there we go. We've already confused our listeners. So
I'm confused all the time anyway. So.
Yeah. Look, I look at my family life and all the plans I came up with when I was 25 years old, and I'm permanently confused. But so CPK of 2, we'll get it right. Is there are 12 standard deviations total in the variation of your thing, your metric, your whole width within specification limits, and the CPK of 1 is only 6 standard deviations. So there's more variation, and you have more higher likelihood of things being outside of your specification limits, which is obviously a bad thing.
Yeah. Well, I'm gonna wave my arms around a little bit and go so if you have the specs, right? You have the lower spec and the upper spec, and they're on a number line of what something that you're measuring. It's on the drawing. It's in the capability or ability to make those measurements to that precision, those kind of things. And you have this number line, and you put the upper spec and lower spec, and you draw those lines. And then you say, well, where's my actual output of this process? Well, let's go measure it. And you measure 30 or 40 or 50 or however many you're measuring, and you do a little histogram. Is it tight and in the middle of those specs, or is it a uniform flat plateau that goes right to the edges of the specs, and you've artfully deleted all of the ones or removed all the ones that are out of spec? It tells you a completely different story with just that simple exercise. Now, the math and the statistics on it then allow you to do a bunch of other cool stuff. And what you want, though, is like a CPK of 2, which means that little histogram or normal curve is half the size of the width of your, assuming you're drawing it to plus or minus 3 standard deviations for your normal curve of your process, it's half the width of your specification. And so if it's centered, it could vary. You get different materials. It gets hotter or warmer. You know that it's going to vary. It's going to have different variation each day, and it's going to have slightly different mean point that it's centered on will vary slightly. That will happen. But because it's small compared to what your specs are, the likelihood of something falling out of specification is greatly diminished, as opposed to if you have a normal curve that touches both sides of your specifications, any variation will dramatically increase the number of things that don't work. And even worse, and I've seen this a handful of times, is you have a very tight specification. This is critical to make this product work. And we have this process that's just not able to make that at all. So maybe 1% of what we produce actually falls in spec. And it's like, well, that tells you a completely different story. Maybe we're using the wrong technique to create this thing.
And going back to that, chat we had about statistical process control, I mean, your machines are going to vary. They're going to age. They're going to wear out. They're going to do things over time. They're not going to stay consistent even when they're operating perfectly, because there's a couple of laws of thermodynamics which are big about this, is that it will change. Your things will eventually wear out in a completely understandable, okay way, and your tools will wear out or change and have variation from lot to lot.
Oh, just the temperature variations, or
exactly.
Just material variations, just the alignment, just all kinds of things that vary. And that's typical. You got to expect that.
That's life.
Yeah. The mechanical engineers knew this years ago. That's why they put plus or minus on their drawings.
Right. That's true.
That's the theory anyway. I read it someplace.
But the idea is that I think that those who are new to this conversation, or even those who are part of it, we have industry standards which are not really based on any sort of defendable theory about what your CPK should be. So, for example, some will tell you, the CPK needs to be 2. We need to be striving to have a CPK of 2. Others will tell you that, if it's an existing process, the CPK needs to be 1.33. If it's a new process, it needs to be 1.5. Why is that high? Well, because it's a new process, so it's going to
it's going to have more variability,
right?
Normal variability, expected variability, I should say. Yeah.
If it's safety-related new process, it needs to be 1.67. If it's a safety-related existing process, it needs to be 1.5. And that's if you have 2 specification limits, i.e., one on each side, a high specification and a low specification. If you just have one specification, well, you've got entirely a new raft of goal CPKs you need to have. The problem with this is they're arbitrary and based on nothing, because the CPK itself essentially tells you, if you understand the math, how many defects you can expect. So I can, plug it into equation, and I can tell you that if a process has a CPK of 2, then you expect 0.002 parts per million to be defective.
Which is pretty low.
Very low. Well, depending on your application. If you have a CPK of 1, that means that 2,700 parts per million are going to be outside of specification. If it's 1.5, 6.8 parts per million will be outside of specification. So when it comes down to it, CPK is actually a different way of saying how many defective products you expect to have. And when I talk to clients and customers and organizations who you might have a combination of statistical process control and process capability analysis, where they find these CPK values and trundle off towards these goals. And they also have demonstration testing to work out, how many parts per million are failing. You go, you know what? If you can throw all that away, work out your system quality goal and use a couple of really simple steps and allocation factors. And for those of you who've done reliability allocation, a very similar process, and essentially come up with CPK goals for each one of your processes. And all you need to do is make sure your CPK for that hole width and the mass and the surface smoothness, or whatever it is, you come up with CPK goals for each one of these characteristics. And if you meet these CPK goals, you're within spec. You just know it. And it makes it a really, really simple, more informed, and just a culturally easier process to incorporate, because instead of having to do all sorts of different qualification tests and demonstration tests and PCA and SPC, you have a single approach where you just have these goal CPKs. And if you meet these goal CPKs, once you've done the underlying theory, you have some more realistic goals, not ones which just appear on page 376 of a textbook. And so, okay, that's what it needs to be. That's nonsense. It's not your organization.
You kind of glossed over a part that we'll probably have to come back to talk is, well, how do you pick the right measures? What is it that you need to measure? Because if you've seen it where organizations measure just about everything. And so their allocation in order to get their overall goal will be CPKs of 12. But in reality, if that part of the process doesn't work, if you have something that fails there, nobody cares. It's not going to affect the performance of the product, and customers never, so some specifications are more critical than others for the overall. So it takes a bit of engineering and work with the design team as to what are the ones that are actually the ones we need to monitor and control. And what are those critical few, I think is a term you like to use. But so there's a bit more to it than just, pick 3 of them and go.
Absolutely.
Because you could pick 3 nonsense ones and spin your wheels all day long and still not make any progress. So there's a bit to it, but the math works great. It's so you can allocate what's the overall defect level that meets our targets for for our product, and let's back that down into our processes, and it's monitor and control those things. And if in that way we don't have to spend a bunch of money and energy to get something to an arbitrary value when it's really not necessary, or vice versa, is identify the areas that we do need to invest in the equipment and improve the process. So it helps make a lot of decisions, and it's a step that I see and I think that's part of the discussion, is there's too many applications where it's just disconnected. The folks on the factory floor are measuring things and they create CPKs, but it's not connected to the design of the equipment or the design of the product. And
sometimes they're trying to chase CPKs, which just don't need to be that high.
Yeah. Well, I have a CPK of 28. Okay. Mm-hmm. That's nice. That's right. Why do we care? Right. Why are you measuring this anymore? What's the point? I remember one discussion with a vendor was, they were saying they're having trouble with the CPK and all that other stuff. And I says, well, what's the issue? And he says, well, the specification's too tight. We can't make it that precise all the time. Our process varies, and it was a stamping process or something like that. And I says, oh, well, let me check where the specification came from. And I get back to the mechanical engineer that specified it, and goes, oh, I didn't really think about it. I just put plus or minus 10% on it, like everything else I don't know about. And well, let's talk about this. Where does it really need to be? And he went off and did a little calculations and scratched his head a little bit and goes, oh, yeah, you could make it, plus or minus, 2 miles, and it'd be fine. And I'm like, okay. Right. And he says, because I knew that process would make a product I wanted, and I didn't really care about the specification. And he says, well, that created a consternation because somebody flagged it a critical dimension, and now they have to measure all this stuff, and they're having fits. So think through that process. It connects from the design intent to what's critical to achieve it to your ability to actually create it. And so measuring the right things in that process allows you to tie those all together.
But it also, the process too, if you go through the math and you say, well, I need a CPK of 3.8 for this particular thing, which is a very high CPK value, then the next step is not, religiously go and trundle off and say, well, we won't stop work until we reach 3.8. If you have one characteristic which has such a high CPK value when you go through the math, then that's where you have that where you do what you did, walk to the designer, say, hey, this characteristic we're having all sorts of trouble with. We need to get a CPK of 3.8 to get there. And some, as you know, some processes can do that, but it's not common. And you would hazard a guess to say, if we have to have a CPK of 3.8, otherwise the wheels fall off, we're not in trouble. So the first thing,
we're going to have to accept more yield and failures. We just have to accept more problems. If we can't achieve it and it's critical, then, well, we got more problems. And we'll have to make 6 parts for every one that we want to use,
But then but that starts the conversation. You know which conversation you need to have. You speak with the designer. He says, oh, it's just plus or minus 10. It doesn't need to be that. We can work around that. Oh, we'll change that, et cetera, et cetera. So, but now you've closed the loop for that particular scenario. Or conversely, you say, oh, no, it really has to be those specification limits based on the current design. So that triggers a conversation where things like yield, things like higher acceptance of risk when it comes to field failures or redesign are then triggered by an actual issue, not a perceived issue that some checklist says matters for this for your design, even though it's just an arbitrary number in a textbook.
Yeah. I think we should come back and talk about this some more because there's a bit more. The more we scratch at it here, is the more elements there's part of it. I think we spent quite a bit of time just talking about CPK. So maybe a part 2 to dive a bit deeper into using it would make sense.
Yeah, absolutely.
All right. So if you're listening to this, hopefully, as a reliability engineer, you didn't turn off the thing or switch over to some other podcast as soon as you heard a CPK discussion, because if you made it this far, then I suspect you already understand that it is a part of a reliability world, right? Whether the quality team does it or the manufacturing team does it, or your vendors make these measurements and get their process under control, it is part of creating a reliable product. And so we should be involved with that process throughout its life cycle. So let us know. Please join the conversation. How's it going for you? Is this part of your role as a reliability engineer? What's working, what's not working? What hurdles are you facing? We'd love to hear from you. We've gotten a number of really good questions over the last couple of weeks and like to add your voice to the conversation. You can head over to accendoreliability.com/go/SOR, and you can leave us a voicemail there, or you can leave us a comment. Chris and I and the other hosts of the show are available and active on LinkedIn or on our About pages. You can leave us comments there. Lots of ways for you to join the conversation. So, our CPK has got to be recalculated for the length of our episodes here, Chris. We kind of got into this one. And that was after talking about it for 10 minutes before we hit record.
That first 10 minutes was the best. For our listeners, they got the tail end of what was started off as a really good conversation.
That's right. Yeah. So we'll come back to it because I think it's still got some meat into this discussion. All right. Thanks, Chris. We'll talk to you again soon.
Likewise, Fred. Always a pleasure.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.